Here are solutions to homework set number 9 for ECE 463-663 Modern Control. This homework set looks at calculus of variations, specifically trying to find the shape of a soap film, shape of a hanging chain, and optimal paths using calculus of variations. Now the first problem is find the shape of a soap film that rotates about the x-axis. The first one is at x equals 0, y is at 10, at 4 is at 9. So what's the shape of that soap film? It's going to rotate about the x-axis. Well, to do that, what I want to do is minimize the surface area. That'll be the y times the length. So here's the length weighted by y. The surface area is 2 pi r integrated along x. This is about the x-axis. It's actually easier if you rotate about the y-axis, kind of switch x and y, in which case this is the surface area spun around the y-axis. Any function that minimizes this functional has to satisfy the Euler-Lagrange equation. So this is f. Here's the Euler-Lagrange equation. If I take the partial with respect to y, that's 0, minus the full derivative of the partial with respect to y prime, since there's no y prime or y, this is 0. If the derivative of a function equals 0, then that function must be constant. So here's the derivative of your functional, the partial. Integrating, that's got to be a constant. Doing some algebra, solving for y prime, I get y prime, that's dy dx, is a over x squared minus a. Pulling the dx to the right, integrating both sides, I get y is the integral of a over x squared minus a, square root dx. A couple ways to solve. If I do a change in variable, let x be a cos theta, then dx is a sinh theta d theta. Substitute for x, pull out the a, cos squared minus 1 is sinh squared, squared gives you sinh, the sinh cancel, and I get the integral of a d theta, or y is a theta plus b. Recalling that x is a cos theta, theta is arc cos of x over a. Y is a times that. Solving backwards, divide or subtract b, divide by a, take the hyperbolic cosine, switch x and y, so instead of rotating about the y-axis, rotate about the x-axis. Here's the form of the solution. Okay, that was a lot of work. So any shape that minimizes the soap film has to satisfy a hyperbolic cosine. To find a and b, plug in the endpoints. When x equals 0, y is 10. When x equals 4, y is 9. So two equations, two unknowns. Solve for a and b. Now personally I don't know how to solve by hand, but I can use MATLAB. I'll create a function called SOAP. I'm going to guess a and b, calculate the first equation, the error in it, second equation, error in it, return the sum squared error. What value of a and b minimize the sum squared error? To do that, I'll use fmin search. So if I say my initial guess is 1, 2, it'll iterate and find out here's a and b. If I start out with 4, 4, it'll iterate and wind up with this solution. This is actually a maximum. That's the minimum. So here's the maximum surface area, unstable equilibrium. This is a minimum. Just kind of a sidelight. What's actually going to happen with the maximum? It's either going to converge up to the minimum, or it's going to go down and snap, in which case you get the degenerate solution. I just form a little ring around the left side, ring around the right side. You won't ever actually stay in this one. That's an unstable equilibrium. So this is actually the shape of a soap film. That's going to rotate about the x-axis and be this shape. Problem 2. Suppose the right endpoint is free. In that case, from before, this is the form of the solution. Plug in the left endpoint when x equals 0, y is 10. At the right endpoint, y prime equals 0. Y prime is sinh, so sinh is 0 at x equals 2. It's going to guess a and b so that the first equation balances, the second equation balances. Find a and b to minimize the sum squared error. So if I try it, you wind up with, here's the solution, that's one solution. That's actually a maximum. Give it a different initial condition, I'll wind up with the minimum, different solution. So here's the maximum. Here's the minimum. This is actually the correct answer. So here's the shape of a soap film when the right side is 2. You notice at 2, these are right angles. And again, the maximum, if I perturb a little bit, it'll either snap up or snap down to the degenerate solution. Here's the degenerate solution, form a soap ring on the left-hand side, and then this part is just snapped. Problem 3. Suppose I want to find the length of a hanging chain. The chain is 12 meters long. It goes from 0, 0 to 10, 1. The length is 12. What is the shape of that chain? Well, to do that, I set up my functional. Here's the potential energy. Lagrange multiplier times the length. Again, the length has to be 12. If I do that, time passes. If you want to see the derivation, go through the lecture notes. This is the form of the solution. At the left end point, this will be the form of it. At the right end point, this has to be 12. Find A, B, and M. Well, to do that, these are nonlinear equations. I can use F-min search. I'm going to guess A, B, and M. The equations then are at the left end point, I'm at 0, 0. At the right end point, I'm at 10, 1. And the length has to be 12. Find A, B, and M to minimize this. Well, throw that in F-min search. Try to find A, B, and M to minimize it. Here's the sum squared error. Basically 0. So you found the answer. There's A, B, and M. And then this is the shape of a rope hanging between 0, 0 and 10, 1 with a length of 12. That's hyperbolic cosine. So that's one use of calculus of variation. You can calculate the shape of a soap film. You can calculate the shape of a hanging chain. Another use. Suppose I have x. I want to go from 6 at t equals 0 to 4 at t equals 10. And I want to minimize x squared plus 4x dot squared. If I just want to minimize x squared, I'll go down to 0 and come back up. Minimize x dot squared, I'll just go 6 to 4. If I want to do a combination of the two, what is that path? Well, this is where calculus of variations again comes into play. Any solution has to satisfy the Euler-Lagrange equation. So taking the partial with respect to x, partial with respect to x dot, taking the full derivative, the solution has to satisfy this differential equation, or assuming everything's in the form of e to the st, where s means derivative, minus 4s squared plus 1 equals 0, means that s is plus minus 0.5. So here's the form of the solution. Plug in the two endpoints. At 0, x equals 6. At 10, x equals 4. Two equations, two unknowns. Solve. Here's a and b. So here's the answer. This is the path that minimizes this cost function. And that's what it looks like. It goes from 6 at t equals 0 to 4 at t equals 10. Last problem. This is leading into controls. If I have a first-order dynamic system, I want to minimize this cost function, x squared plus 9u squared, subject to these constraints. What is the optimal path? Well, here I've got my functional, x squared plus 9u squared, a constraint, so add a Lagrange multiplier times the constraint. I now have three variables, x, u, and m, gives me three sets of Euler-Lagrange equations. Euler-Lagrange equation with respect to x gives me the first equation. Euler-Lagrange equation with respect to u gives me the second one. Euler-Lagrange equation with respect to m gives me the third one. I have to satisfy all three of these, doing some algebra, substituting, multiplying it all out. I eventually wind up with minus 18s squared plus 2.18x equals 0, meaning s is plus minus 0.348. So here's the form of x of t. Plug in the endpoints. At t equals 0, I'm at 6. T equals 10, I'm at 4. Solving for a and b, I wind up with A is 0.11, B is 5.88. So here's the path. If I want to know what the input is, I could solve that. Once to know x of t, I guess from here. X dot plus 0.1x is u. That'll tell me u of t. But here's the optimal path. And that is homework set number 9, calculus of variations. We'll be using that for the next couple weeks to get into optimal control. This is just using scalar systems, first order systems. Expand that to matrix form, I can now handle n by n systems. But that's in the coming homeworks. That's homework set 9 for 463.